In this video, we're going to look at some of the consequences of path independence of line integrals. These results that we'll develop here are useful in a variety of contexts in which multivariable calculus is often used. So to start, let's suppose that we have this line integral over C of the vector field f, and let's suppose it's path independent. On a closed curve C. Now, to be clear what I mean by closed, all I mean is that it has the same initial and terminal point. Right? So for example, if we pick some point to be that initial and terminal point, I want curve C to curve around in the plane or in 3 space and end up right back where we started. So this is an example of a closed curve. So what we want to do is we want to pick 2 points on this curve. We're just going to call them A and B, and they can be anywhere we want. So I'm going to pick point A to be this point here, and maybe point B will be this point up here. And by doing that, I can actually break up curve C into 2 different curves. I can define a path C1 from A to B, so I'm going to do that one in red. So C1 is going to start at point A, follow curve C around to point B. So that'll be curve 1. And then I'm also going to define curve 2 to start at B and to work its way around curve C to A. And so this will be my curve C2. Right? So what we've done here is we've broken up a closed curve C into 2 paths, a path C1 from A to B and a path C2 from B to A. So now if we try to compute the integral over the entire closed curve C of the vector field f, the first thing is we can see, because of how we've broken this curve up, this is simply the line integral over C1 plus the line integral over C2 because we can just follow path or curve C1 and then follow curve C2, and that makes up all of curve C. The second integral here over C2 we can actually think of as the negative of the integral over the negative C2 path. Right? Remember that negative C2, the path, taking the negative just means we're going to take the same path and go in the reverse direction. So I guess I did not draw it on the picture, probably should have. C1 is going from A to B. I know I said it out loud, but just to be clear, C1 is going in this direction, and C2 is going from B to A. So it's going in that direction. So negative C2 is just the same curve as C2, except the arrows are pointing in the other direction. Right? Well, now notice if we have negative C2 and C1, those are both curves from A to B. And we have an integral here which is path independent, which means we don't really care about the path that we take to go from A to B. This line integral is just determined by those 2 endpoints. And so these 2 integrals here that we're subtracting are both equal to the same value. We don't know what the value is. We don't really care. What we care about is that the difference is going to equal 0 by path independence. Right? So what we've seen here is that if we have a path-independent line integral on a closed curve, that line integral must equal 0. Okay? On the other hand, let's suppose we had a line integral with this property. Right? Let's suppose that the line integral over C of our vector field f was equal to 0 for every closed curve C. Right? So we just saw that if we have a path-independent integral on a closed curve, that we will get an integral value of 0. Now we're supposing the integral value is 0 for a closed curve. And so what we might think we could get is we could possibly show that in this context that this integral has to be path independent. And that's exactly what we're about to do. And so what we need to show path independence is we need to start with two paths that start and end at the same points. All right, so let's do that. So let's take two paths, and let's just call them C1 and C2 from point A to point B. So we have two paths starting and ending at the same point, starting at A, ending in B. And from these two paths, much like we just did in the previous slide, we can use these two curves to make a closed curve C. All right, so we're going to define closed curve C in the following way. So it's going to be the curve C1, which will go from A to B, then negative C2, which C2 is a path from A to B, so negative C2 goes in the opposite direction, so we'll go from B to A. So this curve C will go along C1 from A to B, and then back to A along negative C2, so it is a closed curve. Right? So then we know that the integral on any closed curve of this particular vector field is equal to 0. That's our assumption here. But as we just saw, this closed curve C we can think of as the integral over C1 of f dr plus the integral over negative C2 of f dr. Right, just breaking up this curve C into into the two paths that defined it. We can rewrite the second integral in this sum. Instead of as a positive, we can make it a negative, but then we have to switch the orientation on the curve. So if we take the negative of curve, that just becomes the original curve. Right? And think about any kind of path, change its orientation once, and then change its orientation again, and we're simply back to the original orientation of that path. Right? And so we get that this is just the line integral over C1 minus the line integral of C2. Well, if I have a difference of two quantities equaling 0, like I do here, then we must have those two quantities being equal. And so under this assumption that the line integral of f is equal to 0 for every closed curve C, we've shown that for any two paths from an arbitrary point A to an arbitrary point B, the line integrals are equal. What that means is that the only thing that matters would be the points A and B, the endpoints of the two paths. Right? We don't care about what happens in between. And therefore, this integral was path independent. All right, so to quickly summarize everything that we've just done on the previous two slides, we have the following theorem, which is very, very important in vector calculus, and that is the following. It states that the line integral of C of a vector field f dr is path independent if and only if the integral over C of f dr equals 0 for every closed path C. Okay. And so the if and only if part, if you're not familiar with basic logic, if and only if basically means that these two conditions are either both true for a given integral or are both false. So if an integral is path independent, then the integral over any closed curve will equal 0. And if the integral over every closed curve is equal to 0, then the integral is path independent. So one other important theorem relating to these concepts that we're currently talking about that is often used heavily in areas where multivariable calculus is used is the following. Right? So let's suppose we have a vector field F, which is continuous. Right? Recall that a vector field is continuous if its scalar fields that make up the vector field are each continuous. On an open connected region D. I do not believe we've used the word connected before, and I do not believe we're going to use it again. There is sort of a technical definition for a region to be connected, but it is, for our purposes, it is good enough to think of a region as being connected if you can get from any point in the region to any other point in the region without leaving that region. Right? So, for example, if we had any kind of a circular shape or a blob of some sort, we could go from one point in there to any other point without leaving that shape. Whereas if we had two circles that were not, say, the circle centered at the origin of radius 1, the unit circle, the interior of that circle, and a circle centered at the point 0, 10 of radius 1. Right? We have two circles that are separated by space. There would be no way to go from a point in the first circle to a point in the second circle without leaving the region of those two circles. So that would be a non-connected space. All right, so in this case, we have a continuous vector field F on an open connected region D. Right? So if this line integral of C of F dr is path independent, then F is conservative. So I state this theorem, not that we're going to use it, but rather just to sort of finish off what we sort of started with the fundamental theorem of line integrals. The fundamental theorem of line integrals says that if we have a conservative vector field, then that the line integral over that vector field will be path independent. And this theorem, on this little condition that the vector field is continuous on the open connected region, says the converse of that. If the integral itself is path independent, then we must have a conservative vector field to begin with. Okay? So in the next video, we're going to take up this question of determining whether or not a given vector field is actually conservative. In other words, if we have a vector field, is it the gradient vector field for some function f? And if so, how can we find that potential function f?